Today I had such a really good conversation. I had such a really good conversation with this guy at a random coffee shop in Auckland. You know, he had a sign that was saying that I help people with their passions. He had a sign that said, I help people with their passions. Stop by, let's talk about your passions. It's my passion to help other people with their passions. I should have taken a picture of the sign. I thought it was a very creative sign, and I thought it was super cool, and I got to sit with him and chat. And in talking to him, I got to learn that he talks to people, random people, about what it is they're passionate about, especially people that are stuck. Either they don't know what they truly are passionate about, or they're on the journey of pursuing what they're passionate about but are stuck. And so he helps them get unstuck, and he helps them build like a personal brand, really understanding what it is at the core that they're seeking in life and who they are at their core, what he calls their truth. You know, he says everybody has their own truth. And I think it was super interesting because I got to chat with him and got to learn his ideas, and I got to share my story and what I'm doing through this YouTube channel. Man, it was so fun. It was so fun. But one of the things he said to me, which I thought was super interesting, is like, follow your excitement. Because, you know, like, I think sometimes in this journey of like content creation or whatever it is, like pursuing our passions, doing the things that we always wanted to do, like, I think we can get caught up in, how is this going to work? How is this going to work in the future? How am I going to make money from this? And it's easy to lose track of what brings excitement. But one of the things he said is just like, just really follow where the excitement is. Like, what are you really truly excited about talking about? What are you excited about doing? What are you truly feeling excited about? And just follow that. And when you follow that, it brings more excitement, and people are attracted to excitement. And I think some of you guys who are watching this video, you are back on this channel because you saw that I was super excited about algorithms, or super excited about whatever I was talking about and the way that I was explaining it, that you came back. And so welcome back, welcome back. You're my tribe, and you're excited about things that excite me, or you're excited to watch me being excited about things that maybe other people are not excited about. Maybe I just happen to be excited about it in a different fashion, and you're excited about watching me being excited about that, or following me along on my journey of excitement, and that's exciting for you. So yeah, welcome. You're my tribe, you're my friend, and we're gonna be excited together. And today I just wanted to finish the lesson that I was doing on 2 pointers. I think we're done 2 questions, and there were 2 parts left. There were 2 questions left, so I'm going to do those questions right now. And then we're going to move on, because I really want to get to sliding window, and I'm going to show you how sliding window is exactly the same idea. And what I'm doing in each video, I'm showing you how to separate the skeleton from the flesh. I want you guys to get really good at abstracting ideas, because that's the job of an engineer. The job of an engineer is, whenever you get a new problem, you have a way of separating the meat from the bone, right? And then once you have the bone, you can apply it to any new problem you see, because not every problem you're going to see in your life is going to have exactly the same flesh. So that level of abstraction is really just what problem solving is all about. So when they talk about problem solving, they're trying to see, like, if they give you a new problem, are you able to abstract layers that you've seen before? Because you're not going to have seen the problem before, but you've seen the patterns that exist in a problem that you are seeing for the first time. So that's exactly what I'm going to do, but I'm going to show you a pattern that shows up in many other problems, which is called 2 pointers. And I'm going to show you 2 problems that will help you further appreciate the idea that these problems are essentially the same, even if they have different flesh. And I'm going to help you understand and appreciate the idea of applying 2 pointers to those new problems that you're seeing for the first time. But then you can take this approach that I'm going to show you to apply to other 2-pointer problems that you see in the future. And your application will help you be able to solve the problem really quickly in an interview setting, but also be able to solve it in a very optimal fashion. So like we said last week, or a few days ago, I don't know when you're seeing this video, is that, like, yeah, you could take an algorithm that was order n squared to order n by using 2 pointers. So that's what we're going to do in this problem set. All right, guys, let's get started. Let's go. Hey. okay, let's go. That's how I thought coding would be like okay, let me share my screen so we can get stuff to new recording. Let me share my screen, let me share my window, let me show this, and we're gonna start from a blank canvas, like boom, from a blank canvas. All right. Oh, you see, guys, I read the Bible. 1 Corinthians 7:24. That's what my friend sent me. And I've been looking at Afrotech tickets, you know, and Google Flights. And I'm looking at perfumes. And I'm looking at a role that I'm interested in. Yeah, so guys, I'm working, okay? I'm not just out here playing. Like, I'm actually doing work. This is real. This is real time. I'm interviewing as well. I'm still interviewing. Like, guys, like the rest is for the dead. I'm not resting until I get exactly what I want. So let's go to educative. I think we'd already talked about this, guys. I've already shown you the history behind 2-pointers. If you haven't seen this, go back to the previous video. It's titled 2-pointers part 1. So today we're gonna talk about 2-pointers part 2. Now this is fast and slow pointers. What we're doing is, I mean, it's the same thing. It's the same idea, and I already highlighted it for you guys and explained it to you. The idea of 2-pointers, how you have 2 pointers that move, and they can move like this. They can move like this. The only thing that's gonna change in each of those problems. For example, these are 2 different problems that we did last time. So last time we did this one, detecting a palindrome, and we had 2 pointers that were starting. 1 pointer was starting at the beginning and 1 pointer was at the end, and then we'll move them accordingly until we're at the middle, right? And we're comparing at each turn. And we did this problem as well, where you have a target and you're trying to add up 2 numbers to meet the target. And this showed us that even though sometimes we have 2 pointers, it doesn't always mean that they're moving at the same speed. And it doesn't always mean that they're just moving by 1. So sometimes the other pointer may be slower than the other one. That's what we saw in the second example. But it's still the same idea. And that's exactly what I'm going to do with you guys just now. So let's go to Leetcode. And then let's talk about this question. So like I was working from the roadmap, right? So you see how the roadmap, we've done this too. So today I ended up doing this too on my own time, but I'm gonna show you how using the flesh and the skeleton you can get to answer the problem. So let's read the problem, and then I'll go down to it, and I'll show you guys how to do the skeleton and the flesh. So we're told here that this is a 3-integer sum, right? Actually, before I get there, I want to open the one that we did prior. So we did, I want to open all of them, right? So that we remember the things that I was preaching last time. Let's see here. So remember, like the is palindrome, this is kind of how we wrote it. It's pretty simple. But what I want to, shed more light in is like, remember guys, like we had a left is less than right, which we were saying this part here, the external part here, the part that includes the 2 pointers, the part that includes the while left is less than right, and all that logic, for the most part is the skeleton. What then becomes different is how you're managing your pointers, the logic that manages your pointers at each and every turn. At each and every iteration. That's the only thing that really changes. So once you've figured out that a problem set is 2 pointers, then the thing that you need to do immediately is that you need to already restructure your code like this, where you have the 2 pointers. So this is how you end up saving time in an interview, because essentially that these are parts that you can abstract from the problem. And then all you need to worry about when you look at a problem, and next time all you need to think about is like, okay, how am I going to move my pointers on each iteration? And that's exactly what we're going to be doing in this problem. So we already know, without even like reading the question, we already know that we need a while loop with the 2 pointers, and that all we have to worry about in the flesh is how the pointers are going to move given the needs of the question, right? That's all we have to worry about. So like looking at this problem, for example, right? So we're told that you're given an integer array nums, return all the triplets, such that num so that you have num I, num j, num k, and all these I, j, and k, they're all different. They're all different indices. They're all distinct, and you want to be able to add them to 0. So the output should not contain any duplicate triplets. You may return the output and the triplets in any order. I like that. So the triplets and the output, you can return them in any order, but they should not be duplicate triplets. So we need different triplets. So the way that I thought about this problem, right, is that essentially if you look at this problem, it's just a layer above the other problem we just did. So if you look at the problem we did here, we're looking for two numbers that add up to a target. This is looking for three numbers that add up to a target of 0, right? So essentially, we can use this solution to solve this to solve this new problem, just with a twist. So I'm actually going to copy some of this code over, guys, because I wanna show you how. Because my whole point is I want to show you how these problems are essentially the same, right? So here we're being told we're not adding numbers to a target, we're adding to 0, right? And we want all of our numbers to add it to 0. I guess maybe we can just leave it up top here in a comment so that you will see where we're going, and then we can build the solution together. So let's look at this for a second, right? We're being told that we need 3 numbers that add up to 0. In our previous solution, we found 2 numbers that add up to a target of 0 in this case. So we can essentially lean on the solution we already have. But the only difference is we need a third number. So what I suggest is that what we can do is we can still use 2 pointers to get the other 2 numbers. And then we just need to get the third number. The third number could be the index that we're looking at. So what I suggest for this question, or my approach for this question, is because I know about the idea of 2 pointers here, what I could apply the flash then for moving the pointers could just be like, for each index, for each index I need to find 2 other numbers that are complementary to the value of index I. You get what I'm saying? Like, because we're trying to find 3 numbers, what we can do is like, for each number I, for each index I, we can find 2 other numbers between I plus 1 to the end. So that's exactly what I'm gonna do. And then I'm gonna just lean on this solution. So let's get started, right? So what we're gonna do is, let me push this down. So what we're gonna do is, for each number, basically find 2 numbers that when added to current number will give 0. Right, so find 2 numbers. And how do we find these 2 numbers? We already did that earlier. We used 2 pointers. Right, because that's literally the last thing we did, which is this. But our target here is just 0. That's what we're gonna do. And then check if we already have the triplets. We already have the triplet, right? If we have it, return, if we have it, then we don't need to add. If we don't have it, add it to the set of triplets. Or rather, we could just add it to a set of triplets, right? And then we can return an array version of the triplet. So we can have a set. So we don't want duplicates. So we can have a set of triplets, right? Set of triplets that we're adding to, and then we return an array of the triplets. Yeah, this is how I would solve it. This is literally how I would solve it. So let's go about and do it. So let's set is equals to new set. Actually, it's a constant. Set triplets. Triplets is equals to new set. So we have our set here, and then for each number, right? So for each number, so now let's write the skeleton. So what I've been teaching is you write the skeleton. So in an interview, you seem like you know what you're doing by doing this, guys. So we just let write is goes to 0. Sorry, so let left. But we're doing it for each number. So let's say for let I is equals to 0, I is less than nums.length, I plus plus. So we said for each index I, for each element, we want to find two other elements that when we add it all up together, it adds up to 0. So let current is equals to nums at I. So we get the number out, right? So now we want to find sum. So we say now we want to find two elements. So, and this is where we introduce the algorithm we had earlier. I hope this already shows you like how this is the same exact problem. So now we can just essentially copy paste this. This is from our previous problem that allows us to find two numbers that add up to target. So right now we're gonna find three numbers that add up to target, but this is the third number, right? So here we just say find two numbers. So let left, let right is equals to numbers dot length still. So left is actually equal to we're starting at I plus 1. So left will be I plus 1 in this case. And then right will actually be equal to the end of the numbers. So this is not this is nums. So and then we say while left is less than right, we do this magic here. So let me comment that out. So while left is equal to right, then sum is no longer equal to just numbers dot left. It's equal to actually to current plus nums of left, right? Guys, this is code that we wrote for the previous one. It's the same exact code. The names are just different. And if sum is equals to 0, right, then we want to add, I guess, we want to add this guys. If sum is close to 0, I think we had said that find two numbers added. We had written that find two numbers that when added to current, they'll give 0. Check that if we already have that triplet. Okay, so if sum is close to 0, here we wanna do a few things, right? The first thing is that we wanna check if it's in the set. So we wanna say if set. Okay, so maybe let's write here. Let triplet is equals to I think I would want to name these guys. So I could say just to make it clean, let left sum. I could say let left num is equals to nums of left. So I'm not rewriting everything over and over again. Just to keep it clean, guys. I love clean code. Let right num is equals to nums of right here, and then so now sum will just be equal to right left num plus right num, left num plus right num, and it's gonna make the other thing that we're writing cleaner, right? So now all we have to do is if sum is equals to 0, we say let triplet is equals to left num current and then right num, right? And then I think it would actually make more sense to make this a ternary string because it's just more space efficient. So we just make this into a string. So we can say the value of left num in this case, the value of right num, the value of current, and then the value of right num in our string. You see what I'm doing here? I'm just making this into a string. So the right num, because we want to check if it's already in the actually yes, I think because we want to return an array of values. Okay, that's fine. So we check if the triplet is already in the set. So if triplets dot has triplet. If it doesn't have, then we want to add it to the triplets. If it doesn't have the triplets, so we say triplets.add, and then we say left num, current, right num, because that's kind of how we did our triplet string here. Okay, triplets.add left num, current, right num. Okay, I think that looks good. So we're checking if we've already saved that. If sum is equal to 0, and then if sum is greater than 0, then that means, oh, we needed to, we didn't you know, like in the previous question, we had to sort these numbers to be able to use this feature. So let's say nums.sort, we first need to sort them. A, B, that's one thing I had forgotten to do, guys. A, B, and then we need it such that it's in ascending order. So A minus B, that's gonna be ascending order. So we've sorted our numbers, so we know that we can do this. If sum is greater than 0, then we need to say right minus as well, else we say left plus plus, and then we go through everything. That means we're gonna end up with all of our triplets that we want, and then we return array.from the set. That's it, guys. So now the set is called triplets. I think that should do it for us. So let's just clean up this a little bit here so we don't get any marks down in the interview. And then let's just make sure that everything is looking clean. And then we'll do a dry run first before we test it. I highly encourage you guys do that in an actual interview, so that they have nothing bad to say about you. Okay, so again, the idea of skeleton and flesh. So one of the things that I've been advocating for, again, if you remember, is that you abstract every question that you see, because it may not be a question that you've seen prior, but this tool that I'm telling you and I'm teaching you will make it so easy for you to apply patterns to new problems that you've never seen before by abstracting the pattern from each question. So we'll do other patterns later on, but this is the 2-pointer pattern, and this is how you abstract it. So one of the things that we talked about in terms of the skeleton is when you have a 2-pointer, the skeleton is always the 2 pointers. It's always the while loop where you're saying while left is less than right. All you have to figure out, which is the flesh, is for each question is going to be different. The flesh is just the layer on top that they're trying to throw you off on. But the flesh is easier to figure out once you abstract the skeleton. So once you walk into a question and looking at it like, oh, I already have 2 pointers, and now I just need to figure out the rest, and which is exactly what we did. So we abstracted the fact that you can find 2 numbers, right? That's the rule of the 2 pointers algorithm, is that you always, whenever you're given a target and given 2 numbers, and you're asked to find the 2 numbers that meet the target, then you're going to use 2 pointers. For this one, we were asked to find 3 numbers, so we knew that, oh, we just need to, for the 2 numbers, we can use 2 pointers, and then for the other number we just iterate for throughout the list to find that number, and then for the rest we're using 2-pointer. So that's what we did here, guys. Pretty simple, isn't it? Pretty neat as well. So let's just walk through the code. So we're sorting the nums here so that we can use this feature of 2 pointers here, knowing that we can move our pointers accordingly. So we said triplets is equal to new set, so we start with a new set here, because we want all the values of all the triplets to be different, to be distinct, and then we're starting a current, which is I, and then we're going up to the nums.length because we want to process each one. We actually don't need to process each one. We can say nums.length minus 1, and the reason is we're saying we're gonna do current left and right, so we could have said nums minus 1 like here, but it's okay. It's just more optimized for one element, which doesn't matter, right? Really, at the grand scheme of things. Left num is equals to nums dot left, which makes sense. Right num is nums of right, and then sum is kind left num plus right num. And then if sum is equals to 0, then we want to check if the triplet is already in our set. So if triplet has, oh, you know what, guys? Actually, we need a separate set here that we're adding our values to. I guess we can just add our values to the final list, the return triplets, or we can call them the final triplets. I think this is what we want to do, because the triplets in here are we're adding an array version of it, so it's not gonna make any sense. So let's do this. We can just say final triplets dot add if triplets has, and then we add triplets dot add triplets dot add triplets. That's what I will do. So now we know that we're actually adding the triplet. If it's triplets didn't have that, we're still adding it to the triplets. And this is order 1 to check this. So our function in its completeness, because we're doing it for each I, we're doing an n operation, so it's about order n squared. But that's just pretty good, given that it's a threesome. In the brute force approach, this threesome would have been order n cubed, but now we reduce to order n squared. Let's see. Final triplets dot add is not a function. Oh, final triplets dot push. Forgive me, guys. And then we return. We don't want to return final triplets. That's something I need to change here. There we go. Let's see if we can submit it. There we go. Okay, cool. So you guys just saw how we abstracted that function. Hopefully that shows you as well. I wanted to use everything that we had taken from the previous function so that you guys can see that this is exactly the same problem. So if you're still not convinced, let's go to the very last problem so that you guys can clearly see that for sure this is the exact same problem that you've been asked earlier. So let's keep going here. All right, let me just make sure that everything is looking good here. I think it is. So we're gonna continue. All right, let's talk about the second problem. I think it's it's not the East palindrome. It's not the two integer sum. So I think I had opened it. Oh, it's the max water. Like, let me delete this before you guys see it. I don't want you to be. Okay, let me remove this. I'm going to explain it. I ended up just writing it, but I'm going to explain it, and I'm going to explain so let's start with the skeleton, and then let's start with the flesh. So I want you to appreciate skeleton and flesh again. So you're given an integer array heights where heights I represents so you're given an integer array heights where heights I represents the height of the bar. Okay, give me a second, guys. Give me a second here. I need to turn on my light. I love to have that light. I love having that light in the background. It just makes things nice, you know. Okay, so let's see here. So we're given the flesh. So you're given an integer array heights where heights I represents the height of the ith bar. You may choose any two bars to form a container. Retain the maximum amount of water a container can store. So it's still two pointer here, right? Because what we're still looking for is we're trying to find two pointers such that the area here covered is the highest area possible. And I guess we can't sort it. We cannot sort this list though. That's the difference between this and the other one. So like right now we're getting the skeleton. So like the skeleton, it's still two pointers, right? 2 pointers. It's still a while loop, right? Still moving left and right pointers as needed. That's that. And then the flesh is like always thinking about how are we going to move the 2 pointers in this problem. Okay, right, that's all we have to think about in this case, right? So I suggest, so let's just look at the problem. So we're trying to maximize the amount of area here. And how is that being calculated? Let's see. So if we started here, and if our pointer started at here, at this height and this height, it looks like our area here would be this. This would be our area, right? It will be the height of the smallest one multiplied by the width. Okay, so it looks like we're saying area is equals to height of small one multiplied by the width, which is essentially going to be able to be right pointer minus left. And it looks like so we're trying to optimize for, in moving our pointers, we're trying to optimize for finding the highest mean, right? So we're trying to find the highest mean. So like if left, so what that tells us is like if we look at the difference between the mean, the difference between the left and the right is bigger, then we want to move the left. If the right is bigger, move the left, right? If the left is bigger, otherwise move the right. Move the right. That's it. So that's the flesh, guys. And then update the maximum area each time, right? So at each time we want to update the maximum area, and then we return the maximum area. So you see how the skeleton here didn't change. The only thing that changed is how we're gonna move those pointers, and we're moving them accordingly to what's needed here. So let's just go ahead and implement that, right? So we still need 2 pointers. So set left is equals to 0, let right. So you see how this is the same exact code as we had prior. So we can say while left is less than right, this is what we're gonna do. So now that's when we bring in the flesh, right? Because the flesh defines how we move our pointers. So we want to calculate area first, and then we say area is equals to let max area is equals to your maximum amount of water, right? Return the maximum amount of water, so which is the area. Let max area, in this case, let's keep it as 0, right? Yeah, because the highest is always going to be 0, right? Let's see. Yeah, the highest will always be 0. The highest in the beginning before we do it cannot be negative, right? So we can say area is equals to, because we're guaranteed that these heights will always be there. Okay, so we can say area is equals to it's equals to heights. So it's equals to heights of left, or rather heights of right, minus height of left, multiplied by multiplied by left, right minus left. right? I think this would be area, and then max area is equals to area math.max. You know what? Because we want, actually, yeah, we want the mean. Sorry, forgive me for this. We want the mean. We want the mean to be. I didn't follow my own instructions here, so let me step back a little bit. And so we said how we're going to move the 2 pointers. Area is equals to height of small one. Height of small one times the width. It's height of small one times the width. So if we're looking at this, we're looking at height of the small one times the width, and that's gonna be our maximum. That's gonna be our height in each and every scenario. So it's gonna be okay. So let's say let height is equals to we're gonna say math.mean, and then we're gonna get of heights of left and then heights of right. Okay, so we found the minimum between these two. That's our height, and then let width is equals to left, right minus left. That gives us the width. Let area is equals to height times width. Right, so now we have the right area, and then we can say max area is equals to math.mean, math.max of the area and max area, right? And then now what we want to do is now we want to move the pointers accordingly. So if heights dot left is greater than heights dot right of heights of right, then we want to move, if the heights of left is greater than the heights of right, then that means if the right is bigger, move the left. So maybe let's just start with this. So because we have a chance of finding something bigger if we moved. So we say left plus plus. Else we want to move else right minus minus. You see what I did here, guys? So if the height of the right one is greater, then we want to move the left one because we have a better chance. The heuristic is that you want to move something that's smaller, right? Because you have a chance of finding something better than what you were looking at. So the heuristic is that you have a chance of finding something that's better if you move the pointer over, right? So that's what we're doing in this case. If the thing that you've found to be greater is on the left side, then you want to maintain that thing because it's always the height of minimum of the height of the greatest height times the max times the width, which is the right minus left. So yeah, guys, that's about it. That's really about it. You know, again, let's do a dry run before we run it, just to make sure that it's making sense. And then in this case, we want to return, so max heights, we did okay, so now we return the max area in this case. Okay, so let's just run through our code here before we actually run it. So we have a left pointer and then we have a right pointer. This is standard. I don't even look at this anymore. I don't even think about it. Then we have a max area that can change. And then we're moving our pointers starting at the very edges of the array. And then we're checking that we're getting the height. The height that we want to play with, according to the math that we're looking at here, like I said earlier, we want the height of the smaller bar here. That's what's going to determine how much water we can store. Because we won't be able to store water of the higher one if the one on the left is smaller. And so that's what we do here. We find the minimum between the height of left and the height of right. And then that determines our height. And then what determines our width is the difference between the right and the left pointers. and then the area is just going to be height times width. And then the max area would be the max area we've seen so far is always going to be the maximum between the max area we've seen so far and the current area we're looking at, which is what we do here. And then if the height that was highest was on the right side, we keep that, and then we'll move the left one over so that maybe we can find something bigger. And so that's what we're doing here. And then that's what we're also doing here. We're moving the right in any scenario, and then we return the max area. I think this should work. That makes sense to me. It seems like it's running and it's submitted. That's good. Okay, guys, that's all I wanted to show you today. I wanted you to appreciate again how to abstract problems, especially two-pointer problems, into the skeleton and the flesh. In your future interview, you most likely won't see these exact questions, but look out for questions where you're asked to find two elements in your list, especially sorted list. If you're finding two elements that add up to a certain target, you're most likely going to be using 2 pointers. And by the way, binary search is 2 pointers, because that's essentially what you're trying to do in binary search as well. And binary search all the time, most of the time, it's sequential. All the time, it's sequential data in an array form in a linked list. So those exactly scenarios are the scenarios that you would use 2 pointers. I hope this was super helpful for you. If you enjoyed this video, make sure that you like, comment, and subscribe. Make sure to subscribe, guys. I'm trying to grow this channel. I'm trying to add value into the world. So help me do that by subscribing and sharing this with your friends. Thank you. See you in the next one. Bye. Okay, peace and love. Till we meet again.